We've been over the three states of matter, but let's just review. We are familiar with water in all three states. In the gas state, we call it steam. In the liquid state, we just call it water. And when it's a solid, we call it ice. The densities are significant. Solid ice is slightly less dense than liquid water, but they're in the same range. As a gas, much, much less dense. Molar volume, we've got 30.5 liters is how much 1 mole occupies. For liquid water, it's 18, and for ice, it's 19.6. And then when we look at the molecular view, we see a very large difference. In the gas, there's a lot of space in between. Intermolecular forces are only significant at very short distances. The gas molecules are far enough away from each other that the intermolecular forces really don't have any effect at all. In the liquid and in the solid, the molecules are touchingly close. Here they're disorganized and moving relative to each other, but they're touchingly close, and so the intermolecular forces are significant. In the solid form, we see that the water arranges itself in an orderly manner, and there's some vibration of molecules, but they don't move relative to each other. Thank you. So a big difference between solids and liquids is the freedom of movement. Particles in a liquid state have enough thermal energy to overcome the attractions holding them together, but they don't have enough to just go off by themselves. Remember we said that temperature was related to kinetic energy, average kinetic energy of the particles. At a higher temperature, the particles are moving faster. At a lower temperature, they're moving slower. And if you think about Velcro, I know I'm going to be taking my kids to a carnival tomorrow night for Halloween. They always have these bounce houses and stuff. And have you seen those ones where you put on the Velcro suit and you jump onto the wall and you stick on the wall? I've always wanted to try that. I've never been willing to stand in the line. But how is it that Velcro can hold you up? Well, for some people it can. This is true. But if you have enough surface area, Velcro can hold up quite a bit, right? If you have a small amount of surface area, it's not going to hold up much. You've probably all had experiences with jackets or shoes or something where the Velcro just would not hold, right? The piece wasn't big enough and your shoes kept coming undone. So the strength of intermolecular forces, we can think of it a little bit as how much Velcro there is. And so if you have two things that are very firmly Velcroed together, how do you get them apart? You have to pull on them, right? And when you finally get some movement, they're going to come apart. So in the liquid state, you've got these molecules, and they've got enough Velcro that when they're rubbing against each other, they're kind of moving a little bit slowly, and they can't quite get away from each other, because as soon as you break free from one, you're sticking to the next one. And in the solid, the Velcro is stronger relative to the amount of motion that the particles have, and they're basically stuck. They're in Velcro suits, and they're wiggling, they're trying to get free, but they can't. They don't have enough energy to get free. So the particles in solids are just vibrating. If we look at liquids, we can't really compress a liquid because there really isn't any empty space to squeeze out. But gases are very compressible. There's a lot of empty space. And so you can just push the particles closer together, and overall the volume is smaller. We talked a lot about gases in the chapter about gases. Seems like I skipped a slide, but I guess not. Solids are not compressible either. We can classify solids into two categories, crystalline and amorphous, depending on how the particles are arranged. A crystalline solid has a regular repeating order to its arrangement, and an amorphous solid is just sort of random and messy. Amorphous, the prefix a means without, and morph has to do with shape. Amorphous, without shape. We've all seen ice cubes melt. Here's a solid, and if we add heat to that, this solid, those particles are held together by these intermolecular forces. As we add heat to them, what does that do to the movement of the particles? It increases their movement. If you add enough heat, if they move enough, they can break away from each other. Just like the Velcro. If you pull hard enough, you can get that Velcro apart. And so then they are free to move around and the liquid is formed from the solid. It melts. If we continue to increase the temperature and get these guys moving more, some of them are going to have enough energy that they can actually completely break free and get into the gas state. So these particles are moving around, and they will bump into each other, and we said that in ideal gas, there's no interaction between the particles. We also talked a little bit about real gases and how when we get to low temperatures, when these particles are not moving very quickly, then when they collide with each other, they don't bounce off as fast, and there's enough time that those intermolecular forces can become significant. So as you cool this down and slow these molecules down, when they run into each other, they stick, and we get condensation. If we slow this down even further, they freeze into place. They can no longer move around from, compared to each other. Pressure can also affect this. Any questions about what's going on with the different states? Here's a cutaway illustration of a liquid propane tank. So LP gas is liquefied petroleum gas, mostly propane. And so here it is in the liquid. And it stays in a liquid because at high pressure, the molecules are forced together and the intermolecular forces are strong enough to hold them. When you open the valve, that allows the gas up here to escape, and then more gas from the liquid evaporates and takes its place.